So let us now continue with this question. What they are asking is that consider a code only which is having only 4 valid code words. So valid code words are given to us, and now they are asking that if now they are saying is that this code has a distance of 5, and you can easily compute the distance 5 is there or not. How? See, this is the first valid code word, this is the second valid code word. If you see the distance between these two valid code word, it is 5, because I think these are the 5 bits, 5 zeros, and then followed by 5 zeros again, right? So total 10 bits are there, and out of those 10 bits, if you just notice that only 5 bits are changed, so that's why the Hamming distance between these two valid code words is 5. And now between these two is 10, right? Because these 5 are changed, and then again these 5 are changed. But yeah, minimum Hamming distance is just 5. And then similarly, if you find the Hamming distance between this code word and any other code word, then either you will see the Hamming distance of 5, or maybe more than 5. I mean, you cannot see lesser than 5, because they have given their minimum Hamming distance is 5. Now what they are saying is that, so let me even write it, d minimum is 5, it is given to us. Now what they are saying is that if the code word array is this, then what could be the origin code word? This is quite interesting question. Why? Because they are saying, or they are asking, that what should be the valid code word corresponding to this invalid code word. First tell me, if this is your minimum Hamming distance, then what should be, or till what limit you can correct the invalid code words. So if this is your minimum Hamming distance, then you will say that 2t plus 1 should be 5, it is equal to 5. Then you can correct up to 2 bits of error, right? So up to 2 bits of error you can correct. Now if this is the invalid, then if you find the minimum Hamming distance or the Hamming distance between this invalid and the valid code words, then you will say that between these two is 3, right? And between this and this one is, I think, just 2, and this is 3, and between this and this one is, I think, more than 5, right? 5 and 3, 8, probably 8, and between this and this 2 is somewhere around 7 or something, right? So this is 8 and this is 7. So if you find out the Hamming distance between this invalid and any other valid code word, then this is 2, right? So see, you can correct up to 2 bits of error, which means if there is a 2 bit of error, then only you can correct. So it must mean that the correct code word must be this one only, because your channel, I mean, actually it should be given in the question that channel, my channel, the transmission medium is basically not allowing me more than 2 bits of error, right? Then only you can correct 2 bits of error. So basically the correct valid code word must be this one. I hope that is fine. So if you see all the options, then I think the option A is correct one. Now if you ask me that why this is not the correct option, then the answer is that if let's suppose this is the correct option, then the Hamming distance between these two is 3, and then can you correct the 3 bits of error? Then answer is no. With the minimum Hamming distance of 5, you cannot correct 3 bits of error. So that's why you can correct only up to 2 bits of error. So by chance some valid code word is just having the minimum Hamming distance of 1, then you will be confused, right? I mean, whether this is the valid code word or this is the valid code word, in that case you will be confused. But see what I'm saying, that this is the invalid one, right? Whatever is given to you, and there is a valid code word that is basically 2 distance away from your invalid, and you are saying this is the answer. Suppose there is a valid code word that is just 1 distance away, maybe here or here, then what will be your answer? This one or this one? So see, in this kind of scenario can never appear, because your minimum Hamming distance itself is 5. So 2 valid code word cannot be at the distance of 1, or if you consider this, then that cannot be at the distance of 3. So basically this scenario will never appear, right? So I hope you understood. Okay, now let's move to next question. So let's see this question. What they're saying, to guarantee correction of up to 5 bits in all cases. Okay, they want to correct 5 bits of error. The minimum Hamming distance should be 2t plus 1, right? So which means that it should be 2 into 5 plus 1. That's very easy question. So 11 should be your answer. So that's why A is the correct answer, right? Okay, A is the answer. Now let's see this question. This question I have taken from one of the university, and this is one MSQ question. So let's just see what should be the answer. So what they are saying, an error control code with a minimum Hamming distance of 11 is capable of, if the minimum Hamming distance is 11, then you can detect up to 10 bits of error, right? So detecting of 11 bits of error is not possible, but detecting of 5 bits of error is definitely possible. Correcting of 5 bits of error, Can you correct? Yes. See, with the 11, what you can do, you can correct up to 5 bits, because 11 minus 1 upon 2 is actually 5. So you can correct up to 5 bits. Yes, that's also possible. Correcting 11 bits is not possible. So that's why B and C is the correct choice, right? So B and C is the answer. Now let's move to very interesting portion, which is construction of Hamming code, which means that how to construct a Hamming code, right? Given a data word, you want to convert that data word to a code word. So what you need to do, you need to append some of the parity bits. Now let's just check, or let's just revise that how to append those parity bits. So what we will be doing, so basic idea is that we need to use multiple extra parity bits, and we will need to combine these bits in a smarter way, that each extra bit checks whether there is an error in a subset of data bits or not. So you will understand this, that what do I mean by that in just couple of minutes. Okay, I mean what do I mean by that each bit is checking what. Okay, so you will understand this. So suppose that there is a let's suppose there is a data word which is let's suppose something like this, and I want to convert that data word to a code word, right? So this is a given data word and I want to convert that to a code word using the Hamming distance. So what will I do? I will put some parity bits in the position of 2 power. So this is 2 power, I mean let's suppose the position is starting from 1, this is 2 power 0, this is 2 power 1, this is 2 power 2, this is 2 power 3. So I will be putting the parity bits in these 4 positions. And what is the data word that is given to me? Data word that is given to me is this one, right? So I will putting the parity bits here. Now how to construct those parity bits is actually very simple. Let me just call this parity bit as P1. Let me call this as P2. Now you can call it P3, or maybe based on the position, let me just call it P4, which means I'm calling it first position, second position. And see what I'm doing, like I will be basically following this method. So just a second, yeah, I think, okay, that slide I have, yeah. So this is the slide that I have. So I will be basically following this method, where I will be saying this is the position 1, position 2, position 3, position 4, something like this, right? Now what will I say? That I mean this is up to the notation that you want to use. So I will say that the parity bits are, you can say that this is P1, P2, P3. Okay, this is because this is first parity, so you can say it is P1, it is P2, or you can say it is P3, but I will be calling it P4. P4 means like it is at a fourth position. Similarly, you can say it, since it's the fourth parity, you can say it is P4, otherwise you can say it P8 because it's at 8th position. So I will be calling them at P1, P2, P4, P8, or you can call, generally I think these are called P1, P2, P3, P4, but it is up to your choice. And then these are the data bits. So instead of calling D1, I will be calling D3. Instead of calling D2, I will be calling D5. So basically it is P or D. And that this index is basically just representing whether it is the first position, second position, I mean position number, right? So it is D6, D7, this is D9, this is D10, like that, right? So this is the notation that I am using. Okay, now how to calculate these parity bits? Suppose I want to calculate this P1. Now P1 will be dependent on this P1 itself. Okay, what do I mean by that? I will come to this. So P1, and then you take it or leave one, which means you go to this one, leave this P2, you go to D3. I mean you, if I just write the position number, then you just write 1, and then 3, then 5, then 7, then 9, like that, right? And similarly the P2, you take 2, which means 2, 4, 2, 3, and leave 2, which means you leave out 4 and 5, and then take 6, 7, leave out 8 and 9, take 10 and 11, like that, right? This is P2. And similarly the P3 will be take 3, which means 3, 4, 5, and then leave out 6, 7, 8, then 9, 10, 11. So why I am doing so, and what is mathematics, or what is intuition, what is reasoning behind it? This is very interesting, and that you will get to know in just couple of minutes. Okay, like why I am taking some this weird kind of structure. Okay, so basically this is how you design your check bits, check bit 1, check bit 2, check bit 4, or check bit 8, right? This is how you design. You take 1, skip 1, take 2, skip 2, like that, right? Okay. So I hope you now you can generate the code word given the data word. Yeah, I agree that I have not went through the example thoroughly, because this is just a revision session, but just for the first example, let me maybe quickly do it. So if you are just calculating this, then it will be dependent on this one, this one, this one, this one, this one. Suppose you are using even parity, then it means that this is 1, 1, 1, 1. So 1 is coming 4 times, then that's why it is 0, right? Similarly, this will be depending on whatever is highlighted, and then 1 is coming I think 3 times, that's why it will be 1. This bit will be 1. And similarly this bit is basically dependent on whatever is highlighted. So 1 is coming just one time, that's why this will also be 1. Similarly, this will be dependent on these 4, and then it will be just 0, right? So that's how you can calculate these parity bits. It's very easy to calculate the parity bits. So making the Hamming code is not a big deal. It is very easy. Suppose you want to make a Hamming code out of this data bit, then you can easily do, and the answer is given here. Okay, just do it as an homework. Now let's do more reasoning about it. Suppose that I do have a Hamming code with me, and now I say, let's suppose P1 and P2 fail, which means that P1 and P2 do not agree on their parity bit, and let's suppose I have P1, P2, P4. Okay, P1, P2 and P4. So suppose the notation I am using is P1, P2, P4, not P3. So let me just be consistent with my notation, and let me write 4 here. Okay. Now what I'm interested in, basically, suppose that P1 and P2 fail, which means P1 and P2 do not agree and P2 agree, and if I'm not writing P4, it means like P4 agree. Okay, this is P4. So suppose P4 agree and P1, P2 do not agree. Then what they're asking is that they are saying that in this case, which bit got corrupted? Okay, now tell me, P1 is basically taking care of 1, 3, 5, 7. P2 is taking care of 2, 3, and then you leave out 4 and 5, right? And then you take 6 and 7. P4 is taking care of 4, 5, 6, 7. Now, if you are saying that P1, P2 fail, which means error is either in 1, 3, 5, 7 or 2, 3, 6, 7. So what is common? I think 3 and 7 is common. Error is either in 3 or 7. Now you are saying P4 is passing, which means error is not in 7. It means error must be in 3, right? Error must be in third position. So what I'm telling you that based on the parity bit which is passing, which is failing, you can tell the error position. Similarly, if 2 and 4 fail, which means error is either 2, 3, 6, 7. So either in 6 or 7, because of the 6 and 7 are common, and you are saying the P1 pass, which means 7 is not having error, then 6 must be having error, right? 6th position. So basically, based on the combination that you are having, which means if you are saying P1, P2 fail, which means I am saying, let's suppose I am writing it like this: P1, P2, P4. You are saying that P1 fail, P2 fail, and P4 is passing. And for the passing, let's suppose I'm keeping it 0. Then in this case, like you are saying that error is in third bit. Similarly, if P2 and P4 fail, which means P2 and P4 fail and P1 pass, then in this case you are saying error in the second bit, 6th bit. So basically, based on the combination that which one is failing, which one is passing, you tell the exactly one bit where is the error. That's the key point here, right? And how this all is working, I will come to that. But let's take one takeaway from this, that based on one combination, okay, based on every combination of parity bits, we determine exactly one bit where the error occur, right? The error occur. Okay. So I hope you understood this. So that's very, very important point. Now let me move further. Let me just ask this question. Suppose they say that we check the parity bit and discover that P1 and P4 indicate an error. They are saying that P1 and P4 indicate error. So one way is that you write what is P1 dependent on and what is P4 dependent on, and then you take the common, which is, I think here common is 5 and 7, and then you say the P2 is not indicating error, then that's why 7 is not having error, so 5 is answer. So one way is that you will say that 5 is 5th bit, right? 5th bit is having error, and you do all of this calculation. Another way is that what you do, you just sum this up, 1 and 4, and then 5 is the answer. See, earlier also we can just find the answer by summing it up. 1 and 2, 3 is the answer. 2 and 4, 6 is the answer, right? So earlier also we can do the same thing. 1 to 4, then answer is 7. If all of them fail, then you can just check the 7 is common. If 1 and 4 fail, then 5 must be the answer. If 1 and 4 fail, as I just told you, that 5 must be the answer, right? Now, what if only P2 indicate error? If only P2 indicate error and these two passes, then the error is in 2 only. Why? Because these two are saying, if P2 indicate error means 2, 3, 6, 7 have error, but 3 and 7 cannot have error, and similarly 6 and 7 cannot have error. That's why 2 must be having error. So if only P2 is indicating error, then error is in the second bit, like that, right? So basically you just sum up all the parity indexes which are indicating error, and based on that you can find out that where is the error. That's very beautifully arranged mathematics, and that's how we do the Hamming code. And that is why, like I told at the first place, that is why this all of this is basically designed in that way, which means that that whatever we are doing, we are calculating this bit position based on this 1 3 5 7 9 11, whatever we are doing, we are just doing it to make this mathematics simple, that whenever some bit fails, we can just add these two and then finally get the answer. Okay, so maybe I can tell you the intuition that why it is working so. See, suppose that P1 P2 fail and P4 passes, which means P1 and P2 fail and P4 passes. See, P1 is dependent on 1357, P2 is dependent on 2367. Now, one thing you note here, if you write this all of this in the binary format, or maybe in this expansion format, then you will notice that this 1357 must be having 2 power 0 in it. 2 power 0, 2 power 0. See, just see, this 2 power 0 is there in 1357, right? Similarly, this 2367 must be having 2 power 1. Similarly, this 4567 must be having 2 power 2. See, 4, 5, 6, 7 must be having 2 power 2. So basically, this is taking care of everything that is having 2 power 0, right? This is taking care of everything that is having 2 power 1 in its expansion. This is taking care of everything which is having 2 power 2 in its expansion. Suppose if I say these two are having error, right? It means in its expansion, it must be having 2 power 0, it must be having 2 power 1, right? And then I'm saying that it is not, P4 is passing, which means it must not be having 2 power 2, which means 2 power 2 must not be there. It means the answer is just 3, right? So that's simply you can basically find out the answer just by adding. See, if I say that 2 and 4 are having error, which means it must be having 2 power 1, it must be having 2 power 2 in its expansion, and it must not be having 2 power 0. It means you can just add this 2 and 4, right? Which means 6 is the answer. So that's how this mathematics is working. You do not need to know much of this, but if you just know that how it is working, it is fine. But this takeaway is extremely important, and why it is extremely important, I will just tell you that why it is extremely important. This actually lead to very nice formula, which is 2 power r is greater than or equal to m plus r plus 1. And this formula is just driven by this one nice takeaway. Okay, so let me move further. Let's see this question, and after this question we will try to develop that formula. So what they are saying, how many check bits are required for 16-bit data word to detect 2 bits of error and single bit correction? See, whatever we just studied, the way we are making the Hamming code, okay, which means that P1 is taking care of 1 3 5 7 or whatever, right? The way we have just made the Hamming code is just one of the way to make the Hamming code. There are other ways also, okay, and this way, okay, the way we just studied to make Hamming codes is just one of the way. And actually in the class I have proved it, but for the revision session we do not need it. And the way we are actually designing those Hamming codes, this actually leads with the d minimum. The minimum Hamming distance should be 3. The way we are designing automatically leads to the d minimum to be 3. Okay, so which means that the way we have just designed the Hamming code can detect up to 2 bits of error and correct up to 1 bit of error. Okay, so the way we have just studied, this kind of Hamming code can correct up to 1 bit of error, detect up to 2 bit of error, but it's not limitation, which means we can definitely design Hamming codes which can detect more bit of error, which can correct more bit of error. I will tell you one of the example. Okay, but for now I hope you understood this. Now whatever they have given, okay, 16-bit data word, let me say that m equal to 16, m is I am just using for the number of bits in the data word, and can detect, they are saying that 2 bits of error can be detected and single bit of error can be corrected. See, this information is not actually needed. Needed in the sense that they are just telling us that, see, we are also talking about the same way that you have just studied, right? They can detect 2 bits of error and correct up to single bit of error, which means they are talking about the same Hamming code that we have just studied. Now what they're saying, if m is equal to 16, then how many parity bits you need? Okay. So let me just simplify this question. Suppose that you have, let's suppose you have just one data bit, okay, one data bit. Then how many number of parity bits you need? Maybe you will say that you need, I mean, at least you need two parity. Then only you can have say that okay, one data word is sitting here, right? So you need at least two parity for the one data word. I mean, then only just one data word can appear. Suppose you have two data words, data bits. Then how many parity bits you need? I think P1, P2 you definitely need. Then for the 2 and then P4, and then only you can write your second data bit, right? So basically you need two for the two data bits you need three parity bits, right? So let me call it R. R is number of the parity bits, here 2, here 3, and that's what they're asking. Okay, for m equal to 16, how many parity bits I need? Suppose m equal to 7, how many parity bits you need? P1, P2 I think you need, and then 1 you can accommodate here, and then P4, and then you again be needing 2 power 3, right? 8 at 8, so 4, 5, 6, 7, and then 8, and then you again will be needing at 16. I think it is too far. So basically 1 you can accommodate here, you have 7, and 2, 3, 4, and 3 also you need, so 3 you can definitely accommodate here. So I think you just need you can just do with 1, 2, 3, 4, right? So R equal to 4. What about if m is 16? That's what they're asking, right? So for 16, how many parity bits you need? P1, P2 you need, and then one data bit you can accommodate here, then P4, and then I think and then P8, right? 5, 6, 7, and then P8, and then 9, 10, 11, 12, 13, 14, 15. 9, 10, 11, 12, 13, 14, 15, and then P16, and then there will be P62, but I don't think you need P62 because 1 you can accommodate here, and then 3, which is 4, 5, 6, 7, 8, 9, 10, 11. Till 11 you can accommodate here, right? It will be 11th data bit, and you just need 5 more. So you can definitely accommodate 5 more before this P32, right? So that's why you just need 4. 1, 2, 3, 4, 5. You just need 5. Okay. So here R equal to 5 you need. But is this how we are going to solve the question? See, we have seen one observation, right? So the observation was this. Let me just go to that slide, that based on every combination of the parity bit, which means if I say, let's suppose that this is P4, this is P2, this is P1. If I say that P1 fails, P2 passes, P4 fails, then you will say since these two are passing, these two are failing, and then you will say that error must be in the fifth bit, right? So something like this, right? I mean, based on every combination, you can say that okay, error must be in which bit, right? 6th bit. Or maybe if I say that okay, this is just failing and these two are passing, then you will say error is in the first bit only, right? So based on just unique combination of this P1, P2, P4, you are going to tell that error is in which bit, right? So that is the very important observation that we made. And this observation will lead to a very nice formula, which is 2 power r is greater than or equal to m plus r plus 1. How? Let me tell you how. See, let's suppose that there are m data bits, okay, and r parity bits. So total, how many bits are here? Total, there are m plus r plus 1. Sorry, m plus r bits here, right? So where m is your data bits and r is your parity bits. Now, what I'm saying here is that, so total is m plus r. These are the total bits. What I'm saying here is that here r is the parity bits, and these are maybe one parity bit is here, one is here. Let's suppose one is here, somewhere here, right? I mean, let's not worry about the position. Let's suppose these are the r parity bits, just for the sake of simplicity. I mean, it won't matter wherever we take it. And these are the, let's suppose, m data bits. Now these parity bits combination are very useful, which means let's suppose this combination is, let's suppose 0001, okay, 0001, whatever, right? Then it will say that error is in first bit. If it is 0101, it will say error in the fifth bit, like that. So basically every combination tell that error is in first bit, error is in second bit, error is in third bit, error is in fourth bit. So where is the error, right? So every combination, so basically every bit or every combination is telling you that where is the error. Which means that suppose that we have, okay, for example, let's suppose we have r equal to 3, which means that there are 3 parity bits only, okay. These are the parity bits. Now what does this mean? We can have how many combinations? We can have 8 combinations from these 3, which is 2 power 3 is equal to 8 combinations. which means one of the combination will be 0 0 0, another combination will be 0 0 1, another combination will be 0 1 0, another combination will be 0 1 1, like that, right? So these are the 8 combinations we have. Now suppose this combination is saying that there is no error, okay? This combination is saying error is in first bit, I mean, see, in the way we are constructing this Hamming code, the error can only be a 1-bit error, right? I mean, I'm not saying these are the 2 bits error or something, right? These are just 1-bit error, and now we are trying to identify that where is the error. So let's suppose this combination is saying that error is in second bit. See, these are values 0 1 0 means that parity, let's suppose this is P4, parity 4, or maybe like third parity or whatever you want to say, that it is this is 0 means that P4 is indicating no error, P2 is indicating that there is an error, and P1 is indicating that there is no error, right? So it means that these are the indications. Okay, anyway, like I hope you understood. And similarly, let's suppose this means the error is in third bit, which means that these are the 3 bits 1 2 3, and these are total 8 combinations. See, one of the combination is actually not telling any error, which means like it is wasted for us. I mean, it is saying there is no error. So using these three bits only, you can tell the error is in the 7 positions, right? 1 2 3 4 5 6 7, which means that using these 3 parity bits, let's suppose these are the 3 parity bits, you can tell that error is in this bit or this bit or this bit or this bit, this bit, this bit, this bit, or there is no error. Now what if you have 8 bits total? Okay, so see, these are the 7 bits. What I'm saying that r equal to 3 and total, n means total number of bits. Okay, total number of bits. If this is 7, then things are working fine, which means that we are saying that if you have 3 parity bits, and along with that, let me call it m equal to number of data bits, which is n minus r, basically this is 4, right? And you have 4 data bits, let's suppose, okay, which means you have 3 parity bits. Now you might say that parity bit will be here, here, and then here. I mean, I completely agree with you. Let's not worry about the position of the parity bit. I'm just worrying about the number of parity bits. So let's suppose these are the parity bits, okay, and these are the data bits. Now using these 3 parity bits, you can tell that whether the error exists or not, right? I mean, error is in which position? Error is here, or error is here, or error is in this position, this position, this position, this position, this position, or there is no error. Now what if you have one more data bit? Then that's the problem. Why? Because using these 3 parity bits, you can just cover this much bits, which means you can say that okay, error is here, or error is here, here, like that, right? You will never be able to tell if there is an error at this position, which means that using these 3 bits, you can have only total 7 bits, right? Which means 4 data bits. But if you have more than 4 data bits, then you will not be able to tell the error, right? I hope you understood. So basically, using these 3 parity bits, you can have, or you can have 4 data bits, something like this. Now let's just generalize it, okay? Which means using the r parity bits, how many data bits I can have, right? This is my question. Number of data bits I can have. See, how many combinations I have? Let's just first talk about the number of combinations. Number of combinations using parity bits equal to 2 power r, because these are the r parity bits. That is why if these are the total number of combinations you have, it means that, let's suppose the combinations are like this 0 0 0 0 0 0, right? I mean, this is one of the combination. I think this is too many zeros, but yeah, this is one of the combination. Let's suppose this is another combination, and these are the total r bits, right? I mean, these are the total r bits, and you have total 2 power r combinations, right? And finally this will be 2 power r combination. So total 2 power r combinations you have. Now let's suppose this is telling you that error is in first bit, or I mean, let's suppose it is telling you no error, something like this, right? It is telling you error is in which bit or not, right? Now if there is m data bit, which is what I want to find, then there will be m plus r total bits, right? M plus r total bits. And if the error could be of 1 bit, then how many possible corrupted data words are possible, or the code words are possible? See, if this is having, let's suppose, m plus r bits, then this can be converted to same, which means there is no error, or the error is in first bit, right? First bit, error in second bit, something like this, error in second bit. So basically you can have m plus r plus 1 combinations. So these combinations could be m plus r plus 1, right? So this particular code word can be converted to any of this, right? If there is 1 bit of error, up to 1 bit of error. 1 bit of error does not necessarily mean there will be error, right? And 1 bit of error means up to 1 bit of error. Either there is no error or there is 1 bit of error. If there is a 1 bit of error, then the error could be in the first bit, second bit, third bit, like that, right? So these are total m plus r plus 1 combinations. Now what you need to do, you need to identify that which of the combination is there. See, you have total 2 power r combinations of the parity bits, and each combination identify one of this case, right? So this 2 power r should be greater than or equal to m plus r plus 1. Why? Because these are total combinations that you have. I mean, this is your capacity, right? And this is what channel can do. Your capacity is basically saying that you can detect 2 power, like, I mean, you can differentiate between 2 power r different combinations, right? If there are, I mean, 2 power r different patterns, among 2 power r different patterns, you can differentiate, which means that if there are r parity bits, then you can generate 2 power r combinations, and then you can say that this let's suppose this is one of the combination. This combination is saying no error, right? And this combination is saying, let's suppose, error is in first bit, like that, right? Error is in first bit. So basically you have 2 power r combinations with you, and what is the possibility? I mean, the channel can destroy your particular code word into m plus r plus 1 possibilities. So you should be able to identify that which one of this, which means that whenever you are sending some code word, that at the receiver side, let's suppose it is sender, at the receiver side, let's suppose you are sending C and you receive C prime, okay? This is the received code word, Now this received code word could be same as the original code word, or could be different, right? This is receiver. Now you need to identify whether this is same or different. So basically, whenever you are sending something, then you may land up into total m plus r plus 1 possibilities. I mean, you will say there is no error. This is the error is first bit. No error means it is same as C, right? Error in first bit, like that. So here you have total m plus r plus 1 combinations. Now receiver should be able to identify that which of this combination you have just received. Now what you need to do, using these parity bits that you have, it will tell you that which of this combination is there. For example, let's suppose you have 5 parity bits, okay, which means you have 32 combinations with you. Now let's suppose 0 0 0 0 0, this is one of the combination, 0 0 0 0 1, this is another combination, 0 0 0 1 0, another combination, like that. You have 32 combinations with you. And let's suppose, okay, for hypothetical example, let's suppose you have just 3 data bits, okay, which means along with this parity bits, you can have just 9 different combinations, which means like whatever data bits you are sending, these are the 3 data bits, along with, let's suppose, okay, hypothetically you are sending 5 parity bits, 1 2 3 4 5 parity bits, and this is these are the data bits. Then at the receiver side, you can have, since this m is 3 and r is 5, you can have total 9 combinations, which means you can receive this as it is. Maybe the error is here, maybe the error is here, like that, right? So you have total 9 combinations. Let's suppose it is saying no error, and let's suppose it is saying that error in first bit, it is saying error in second bit, like that, right? But since you have 32 combinations here and you just have 9 total possibilities, which means you will eventually be running out. No, I mean, you don't need these 32 possibilities, which means like I can just tell you that this is 9, right? So I think 9 is this, the 2 power 0, 2 power 1, 2 power 2, 2 power 3 plus 1, right? This is 9. So basically, let's suppose this combination is saying error is in last bit. Okay, something like this. Now whatever the combination you have here, okay, these are the combinations which you actually don't need, but you anyway have it. Now what you can do, you can assign this combination to any one any bit of the error, which means you can say that okay, these two are basically saying, you can say okay, these two combinations are saying that error is in the first bit. That's also fine, error is in first bit, because you have multiple representation with you, which you actually don't need. You just need 9 representations, but since you have multiple, you can assign multiple, which means if you have more combinations with you, see, this is your capacity, this 2 power r is your capacity, right? This is 2 power r, this is your capacity, and channel can destroy into m plus r plus 1 positions, m plus r plus 1 positions. Now what you need to do, whatever is the capacity you have, so you will say that okay, this should be like that. This will tell me that the error is in this position, exactly this position. This should not be confused that error is in this position or this position, right? I mean, let's suppose this is saying that, and this is saying no error, and this is saying error is in first bit. Now each of this should be like this. I mean, this should be, I think, 1 to like I can say, yeah, ultimately it could be many to 1 also, but let me just talk about 1 to 1, which means like this should not be confused. It should always say that okay, error is in this bit. I mean, it should always say that error is where. Now this can also say that error is in third bit, right? Like that, I mean, and that's not a problem. But it should not be like this, that it is getting confused. It should not be like this. It should not be like this, that okay, it is getting confused that error is in this bit or this bit. No. Every of the parity bit combination should be telling you the exactly 1 bit of the error, like where is the error, okay? So that's how it works. I hope you understood. So that is why 2 power r should be greater than or equal to m plus r plus 1. So that's very nice formula. I mean, we have just derived this formula. Maybe you can just remember this formula, and if you know the intuition, then you can even derive this formula, right? Now that's very nice formula. Now let's solve this the earlier question using the same formula. Okay, so yeah, this was the question. So we have just derived that 2 power r should be greater than or equal to m plus r plus 1. Now they have given the 16 data word, which means they have given m value to be 16, and then they are asking what is the value of r. So what should be the value of r? I mean, the minimum value of r, obviously, like how many check bits are required. So you can say the minimum number of check bits, right? If you put r equal to 1, then obviously it is not satisfying. If you put 2, then the 4, and I mean at least the 4 you need to put, because this is 16. Then 16 is greater than or equal to 16 plus 5, which is not satisfying. So r equal to 5 will satisfy this. So that's why this 5 is the answer, right? Using this formula also you can directly do it. Now from now on you can remember this formula. Okay. That's very nice question, and the purpose of this question to make you sure that you can do this question without even knowing the formula, and if you know the formula, then it is even better, right? How to do it without using the formula, that we have just seen. Okay. Now see, this formula is extremely useful. 2 power r is greater than or equal to m plus r plus 1. Now let's just see few more questions using the same formula probably. Okay. So let's just see this question. What they are saying: what is the minimum number of redundant bits are required for the Hamming code for the correcting all possible 1 bit of error if the message is of 27 bits? See, correcting all possible 1 bit of error, it is just a way of saying that whatever we have been studying, they're talking about same kind of Hamming codes. Okay. Anyway, so here you can apply this formula, m plus r plus 1. M value is given to be 28, then I think r equal to 6 will satisfy, right? Minimum value of r equal to 6 will satisfy. So hence 6 is the answer. Minimum number of redundant bits required. Okay. Now let's see this question. This question is very nice, extremely nice question, very good. Okay, very good question which I have taken from MIT. Let's see this question, and what they are saying is very, I mean, this question is very thought provoking, and once you solve this question, you will get to understand the formula, the derivation, and everything very nicely. So what they are saying, let k be the minimum number of parity bits. Parity bits needed to correct all possible t bit of error. See, they are saying correct all possible t bits of error. That's something nice here, right? So they want to correct t bits of error. Earlier we were just correcting 1 bit of error, right? Then which of the following must satisfy? So let's suppose that r is the number of parity bits. Okay, they are saying k. Anyway, let's take it k. So they are saying k is the number of parity bits. And like according to their notation, this n is the total. N is total bits. So m, which is your data bits, are coming out to be n minus k. Anyway, so what they're saying is that you want to correct t possible bits of error, which means the possibilities at the receiver side, right? Possibilities, pardon my spelling, at the receiver side, there could be no error. There could be 1 bit of error. Now there could be 2 bits of error also. 2 bits of error. Similarly, there could be t bits of error also. T bits of error. Right? That's very interesting point. Now this is okay. Now in 1 bit of error also there are how many possibilities? There are m plus r possibilities, right? Here also you have m plus r possibilities, where you will say the error is in first bit. Error is in. So let's suppose that total n bits are there. So there are n possibilities if the total number of bits are n. Error is in first bit. Now error is in second bit. Similarly, error is in nth bit. Now if there are 2 bits of error, then how many possibilities are there? NC2 possibilities are there, right? If n is the total number of bits, then if there are 2 bits of error, then these many possibilities are there for just 2 bits of error. Similarly, for t bits of error, you have NCT possibilities. So how many total possibilities you have at the receiver side? You have no error plus 1 bit of error plus 2 bit of error plus 3 bit of error. Similarly, t bits of error. Now, what is your capacity? If you are having k parity bits, then you can say that you have total 2 power k combinations with you. And these are the total possibilities that they have. So, this 2 power k should be greater than equal to whatever is the possibility at the receiver side. So, let's just see the answer. 2 power k should be greater than equal to 1 plus nc1, something like that, right? So, I think D is the correct answer. I hope you understood how we are solving this question, right? So 2 power k is the total parity bit combination that you have, and these are the possibilities at the receiver side. So that is why 2 power k should be greater than equal to 1 plus nc1, nc2, similarly till nct. Okay, that's very nice question. I hope you understood this question. If there is any doubt, you can just comment it out. I will just clarify that doubt. Now let's see this question. What they are saying: consider 3-bit error detection and 1-bit error correction Hamming code for 4 bit of data. So m is given to you, which is 4. And then they are saying that they want to correct 1 bit of the error. Okay, so see, they are saying that they want to correct 1 bit of the error and they want to detect 3 bits of error. So what do you think should be the Hamming distance? So what they are asking actually the extra parity bits. So they are asking about the r, and they are also asking about the d minimum, that what should be the minimum Hamming distance such that 3-bit error detection is possible because of the minimum Hamming distance of what? See, to detect 3 bits, you need minimum Hamming distance of 4. But to correct 1 bit, you also need minimum Hamming distance of 3. So which means that this is maximum. So you can take the maximum, which means you will say that you need 4 bits of the minimum Hamming distance such that you can detect 3 bits and you can correct 1 bit. So this is required to detect 3 bits, and eventually you can also correct 1 bit. I mean, that's the complementary part that you are having. Now, this is the one part of this question. Another part is saying what should be this r. See, this r is basically number of parity bits. If you want to find out the number of parity bits or number of the check bits that is required, for that you do not need to care about the detection. I mean, you want to detect 3 bits of error or what. You only care about the correction. You want to correct one bit of the error, which means at the receiver side there could be either no error or there could be 1 bit of error. In 1 bit of error also there are different types, right? Or there could be 1 bit of error. So here you are having m plus r possibilities, right? M plus r possibility. Either error is a first bit, second bit, like that, and this is just one possibility. So I mean, you will be using the same formula, which is like this. So if you put the value of m, which is 4, now you will say 4 plus 1 plus r, 2 power r. So I think this r should be this should be 2. No, it should be greater than 2. I think at least 3, right? Yeah, r is 3. So you can find out this r, which is 3, and then the minimum Hamming distance is coming out to be 4, right? I hope you understood. So basically, to find out the number of parity bits, you do not need to worry about the error detection. You only care about that how many bits of error you want to correct. Okay, actually, I mean, everything is connected very tightly. So if you are having, let's suppose if you want to correct t bits of error, t bits of error, then the way you construct, okay, the way you construct your Hamming code will automatically, I mean, you first of all, you need 2 power r should be greater than or equal to this much. That's what we have seen. And the way you construct your Hamming code will automatically make sure that you are having d minimum should be your 2t plus 1. Basically, if you want to correct t bits of the error, then your d minimum should be 2t plus 1. And the way you construct your Hamming code, I mean, there must be some way, and we have not seen that way. I'm not saying that we have seen that way. I'm saying that we have not seen that way. That's perfectly fine. But your way should be confirming that d minimum is 2t plus 1, and then your r should be greater than or equal to this. I mean, you should be satisfying this condition also, right? So everything is tightly coupled. And if you want to correct t bits, then your d minimum is this, and then automatically you detect detect 2t bits of error, right? 2t bits of error. Okay, I hope you understood. Now let's solve this question. If you want to detect 3 bits and correct 1 bit, then to detect 3 bits you need 4, to correct 1 bit, right? Here you need 4, to correct 1 bit you need 3. So that's why you need 4 here, right? And if you want to detect 3 bits and correct 2 bits, so here you need 4, here you need, this is to correct 2 bits, here you need 2 into 2, 4 plus 1, 5. So that's why the final answer is 5, right? Okay. So I hope you can do these easy questions. So this is just an easy question. You can just try it out. Again, this is another easy question. So so now we are going to just see another type of error reduction, which is called CRC. I mean, these are the easy questions, so that's why I'm leaving it out. And in the next video we will just start with the CRC, which is cycle redundancy code. It is also a block code. Okay. I hope you understood Hamming code. If there is some doubt, just comment it out. If you like this session, just let me know. I mean, just comment it out and let me know if you have understood everything, whichever I have explained. Okay. In the next video, we are going to see CRC. Yeah. Thank you.